Hello everyone. What we're gonna do now are continuous random variables. I know my class, we've already done a lot of chapter 5. So this beginning part will be a review for you. The other class, this is where you had left off, so we're gonna start over here. Okay? So you all know what discrete random variables are. They're functions on the sample space whose range is a discrete set. So you have a countable set that is the range of the random variable. In this case, what we're going to look at is situations where the range of the random variable is uncountable. Okay, so what is a continuous random variable? A continuous random variable, you have that the range of the random variable is an uncountable set. All right, so for example, what can you think of that are continuous random variables? You could have heights of people, weights of people, the time it takes you to run a mile. All of these things, the range is continuous. It's not just that you can take exactly 7 minutes or exactly 8 minutes. It's not a discrete set. This is a continuum of numbers that time it takes you to run a mile can be. Okay, so more formally though, a continuous random variable, you say a random variable is continuous if you have a function on the real line that gives you probabilities for the random variable. Okay, this function is called the probability density function of the random variable x, and this is what we have as a definition. So we say a random variable x is continuous if there is a non-negative function on the real line such that for any subset B of the real line, we have that the probability that x is in B. So if you look at the set of omegas where x of omega is in the set B, that is given by the integral over B of this function. Actually, I didn't write it here. F. And so B could be an interval, B could be the whole real line, whatever you have. You get the probability that the random variable x takes on a value in B is given by this integral. So of course, this over here is the analogous function you have like you did in the discrete case. You had the probability mass function. In the continuous case, we have this function f, and f is called the probability density function. Okay, so now recall what you had in the discrete case. You had the probability mass function. So what did you have? You had that the probability that x equals 3 will just be the probability mass function evaluated at 3. It's little p of 3. This is a continuous random variable. And what we look at sets B, and that's given by the integral over B. So for example, what if you looked at the probability that x is any number between negative infinity and infinity? What will this be? This will be from negative infinity to infinity f of x dx. Now, just don't look at the right hand side. Just take a look at this. And what do you expect this to be? The probability x is any number. Of course, you'd expect this to be 1. So that's one of the properties you have of the density function. That's the integral from negative infinity to infinity of f of x. This should be 1. Of course, we already have that f is a non-negative function. For any set B, the probability that x is in B is the integral over B. You have the integral from minus infinity to infinity of f of x dx is 1. Okay, so what if you're asking the question, what is the probability x is between A and B? Well, that will be integral from A to B of f of x dx, just following this property above where we're taking the set capital B to be the interval A to B. Okay? And for example, what if you're asking the question, what is the probability x is some number A? Well, that'll be the integral from A to A of f of x dx. And as you all know, the integral at a point is 0, so you have that this is 0. So for a continuous random variable, the probability that x is any particular number is 0. You cannot just take any particular value and expect to get any positive probability of the random variable being that value. If you take an interval, well, then you have a chance of having something greater than 0 where you're integrating f over that interval. Okay? So these are the main properties you have of the probability density function. It's non-negative. For any set B, you have the probability x is in B is the integral over B of the function f. The integral over the whole real line is 1. The probability x is in any interval is given by the integral over the interval. The probability x is in as equals any number is just going to be 0 by this properties. Okay, so now let's take these and let's try and look at an example. Okay, so we're gonna take an example where we're gonna look at the lifetime of a car. Okay, so here we go. The density function of the lifetime of a certain type of car in years is given by the function f of x, which equals c times x to the negative 3 if x is bigger than 10 and it is 0 otherwise. So what does this tell you? Just taking a look at this, you can see that the probability that the car dies before 10 years, that is 0. Okay, that's what this tells you. Anyway, so what's the question asking you? 1, find the value of C. And 2, if you have 3 such cars, what is the probability that at most one fails in the first 15 years? Okay, so those are the questions that we have to answer. All right, so let's take a look. So first thing is we have to find C. So let's try and find C. How will we find C? Take a look. Here's the density. It is C x to the negative 3 for x bigger than 10 and 0 otherwise. We want to find C. What do we know about f? We know that the integral from minus infinity to infinity of the density, this needs to be 1. That's a property of a probability density function of a continuous random variable. Okay, so let's plug this function f in, and since it's 0 to the left of 10, we know that this will just be 0 from negative infinity to 10, so we don't even need to write that. And from 10 to infinity, the function f of x is cx to the negative 3. Okay, so this is what we have. We have that this integral needs to be 1, so let's sort that out. What will the antiderivative be? Cx to the negative 2 divided by negative 2, and we need to evaluate it. Actually, really technically, we should write this as a limit from 10 to b and take a limit as b goes to infinity. Okay, let's plug all that in. Limit as b goes to infinity of c over negative 2x squared. Sorry, let's plug in the b. B squared minus, so minus of minus will become plus c over 2 times 10 squared. Okay, and as b goes to infinity, you know this will go to 0. So this is c over 200, and that needs to be 1. So that tells you that c equals 200. All right, so that's the first part. We found the actual density of the random variable, and it's not just c x to the negative 3. We now know that the c needs to be 200. Okay. All right, so now let's answer the second question. Say we have 3 such cars. What is the probability that at most one of them fails in the first 15 years? Okay, so take a look at this. What do we have? We have 3 separate cars. And we want to know what's the probability at most one fails in the first 15 years. So this, as a big picture, the question is a binomial random variable question. And what we need is to find the probability that any one of those cars fails in the first 15 years, and that will be our P for the binomial random variable in question number 2. So first, for question number 2, first let's answer the question. So first we'll find the probability that any one of the cars, or actually really I shouldn't name it like that, that a car fails in the first 15 years. Okay, so we want the probability that x is less than or equal to 15. So from the properties of the probability density function, what will this be? This will be the integral from negative infinity to 15 of the density, correct? Right? Because what is this? This is x is less than or equal to 15. So you can think of this like this. X is bigger than negative infinity, less than or equal to 15. Okay, you can think of this like this. Okay, so but you know that the function f is 0 to the left of 10. So you could just write it as 10 to 15, integral from 10 to 15 of the density. Okay, so what is that? Integral from 10 to 15 of 200x to the minus 3 dx. We found out that the value of c was 200. Okay, let's take the antiderivative. That'll be 200 x raised to minus 2 divided by negative 2, evaluated from 10 to 15. Okay, so that's minus 100 and over 15 squared minus of minus, so plus 100 over 10 squared, which is 100. Okay, so what is this? It's 1 minus 100 over 225. All right, what is 100 over 225? 25 goes 4 times and 25 goes 9 times. So this will be 5/9. So this is the probability. 5/9 is the probability that any one car fails in the first 15 years. Okay, so now what do we have? We have 3 cars. And we want the probability that at most one fails in the first 15 years. Okay, so what is this? Let's say y is the number of cars that fail in the first 15 years of these 3. So what kind of random variable will y be? Y will be binomial with n equals 3 and p equals 5/9, as we saw. Okay, the question asks, if you have 3 such cars, what's the probability that at most one fails in the first 15 years? Okay, so what are we asking about 1? Y, we want the probability that y is less than or equal to 1. All right, what is that? We know that's the probability y equals 0 plus the probability y equals 1. All right, so just apply what you know about the binomial random variable. This is 3 choose 0, p raised to 0, 1 minus p raised to 3 minus 0, plus 3 choose 1, p raised to 1, 1 minus p raised to 3 minus 1. So that's what you have. Okay, so you have 4 over 9 cube. 3 choose 1 is 3 times, what do we get? 5 times 16, it is 80 over 9 cubed. Okay, so 4 cubed is 64 plus 240. That's 304 over 9 cubed. All right, or if you want, you can write it down. 304 over 729. That's the answer to part B. Okay, so what are the main things you have over here? You have a probability mass function instead of a probability density function. And the probability that the random variables, any one number for a continuous random variable is 0. And the way you find the probability that the random variable belongs to any set, you have to do an integral. Okay, so that's what we have for the continuous case. Now, one thing that I find useful in explaining this is, and this works for both the continuous and the discrete case. Okay, so say here's your real line. All right, there's 0 and so on. Now in the discrete case, you can think of this. Say somebody has a whole basket of a lot of gold pellets. Okay, and all these gold pellets, the weights of all these gold pellets adds up to 1 gram. All right, so there could also be infinitely many gold pellets. So for example, you could have one which is half a gram, another which is a quarter gram, another which is 1/8 of a gram, 1/16 of a gram, any such thing. So it could be infinitely many such pellets or finitely many such pellets. So say you have a basket full of some gold pellets whose weights add up to 1 gram. Now someone goes along and takes these pellets and puts them at places on the real line. So for example, you could go to minus 253 and put a gold pellet over there that weighs, this doesn't really matter, let's say it weighs 1/10 grams. Then somebody goes to minus 194.96 and put some gold pellet weighs 1/40 grams or whatever such thing. So you're going to different places and putting a bunch of gold pellets here and there, and the total weight of all of these gold pellets adds up to 1. And what these weights of gold pellets at the different places, they represent the probability mass function. So for example, over here at minus 220, there's no gold pellets, so the probability that the random variable equals minus 220 is 0. The probability that the random variable equals minus 253 is the weight of the gold pellet over there, and that is 1/10. The probability that the random variable equals whatever, for example, let's say this is minus 20, and let's say there's a gold pellet whose weight is 2 over 59. So the probability that x equals negative 20 is 2 over 59. Of course, all the weights of all the pellets that are from the basket, they're distributed in the different places. They add up to 1. So this, you can think of this in the discrete case as the probability mass function. And since it's coming, I will just say it right now. For the cumulative distribution function, the CDF, what you can think of as a CDF is, imagine that you're starting at minus infinity. I know theoretically that's not possible, but just imagine that. You're going from minus infinity, and what you have with you, let me try and draw this, is you have a vacuum cleaner, okay? And you're vacuuming and going along, and you're vacuuming all the gold pellets. The CDF, you can think of, what is a CDF, for example, at negative 200. This you can think of as how much you have vacuumed up to the point negative 200 and negative 200. So the amount in weight of the gold pellets you have accumulated till that point. Okay, so you can think of that as the cumulative distribution function. Cumulative, that means that word comes from accumulated. So how much have you accumulated from minus infinity to minus 200 is what you have is the CDF. Okay, so now let's look at the continuous case. What do we have in the continuous case? In the continuous case, you can think of the person not having gold pellets, but let's say the person has this very, very hot urn. Or maybe like a watering jug or something, a very hot one. And what this does is it has molten gold in it. Okay, and this molten gold, totally the weight of this is 1 gram. And what someone's doing now is taking this molten gold and starting at minus infinity and at different places pouring some molten gold all along. Okay, now so you can think of this like a function on the real line. Okay, so if you pick any point and look at the amount of gold over there, well, any sliver of it, infinitesimally small, that'll be 0, just like we needed that our density is 0. But if you take any interval and you ask yourself, how much gold did I accumulate in between over there? That'll be the probability of the random variable being in that interval, and that you can get by integrating the function. Okay, so this is like a density of gold. Like some of you might have learned in physics, the density of a rod is given by so-and-so function. What's the weight of the rod between the points 2 and 3? Then what do? You integrate the density from 2 to 3. So that's why the name, the probability density function. Okay, and once again over here the CDF is, here you go, once again you're going along with your vacuum cleaner and you're vacuuming up to a certain point. How much gold have you vacuumed up? Okay, so yeah, maybe this vacuum cleaner too has a way to melt this gold if it's solidified, and up to a certain point, how much gold have you vacuumed up starting from minus infinity, even though it's theoretically not possible. Okay, so that's, I like this analogy with, trying to vacuum up from minus infinity to a certain point to explain the cumulative distribution function, both in the continuous and the discrete case. Okay, so we're done with 5.1, and with that, I will end this video. The next video, we're going to continue with 5.2. All right, I hope this made sense. And of course, please email and send any questions that you might have had from this.